Assalamualaikum everyone. My name is AINUL MARDHIAH binti ABDUL HAKIM, matric number 307741. So today I will present question 1 and question 2, which are the scenario description and the formulation of the system of linear equation. For our project, we selected a university cafeteria production planning scenario. This scenario was chosen because it represents a real-life situation where management needs to make a decision while dealing with the limited resources. The university cafeteria is preparing food for a large student event. Since a large number of students will attend the event, the cafeteria must carefully plan its production to ensure that enough food is prepared without exceeding the available resources. The cafeteria offers 5 different food sets, which is chicken rice set, fried noodle set, sandwich set, burger set and pasta set. Each food set requires different amount of labor time, ingredients and packaging materials. Therefore, the manager must determine the appropriate quantity of each food sets to be prepared. The objective of this study is to determine the number of food sets that can be produced while satisfying all the resources constraints. To achieve this objective, we use a system of linear equations and represent the problem using concept from linear algebra. Next, we define the variables used in our model. Variable x1 represents the number of chicken rice set produced. Variable x2 represents the number of fried noodle set produced. Variable x3 represents the number of sandwich set produced. Variable x4 represents the number of burger set produced. Variable x5 represents the number of pasta set produced. To ensure efficient resource allocation, the cafeteria must satisfy 4 constraints. The first constraint is the total number of food sets prepared. The cafeteria plans to prepare a total of 100 food sets for the event. The second constraint involves labor hours. Based on the available workers and preparation time, the total labor hours required must equal to 180 hours. The third constraint involves ingredients usage. The available ingredients are limited to 185 units. The fourth constraint involves packaging materials. The total packaging resources available are 235 units. This constraint represents the limitations faced by the cafeteria and will be translated into mathematical equations. Based on the variable constraint discussed earlier, we can formulate the following system of linear equations. The first equation represents the total number of food sets prepared, which is equal to 100. The second equation represents the total labor hours required for producing the food sets. The third equation represents the total ingredients unit used. The fourth set equation represents the total packaging materials consumed. Together, these 4 equations describe the relationship between the 5 variables and the available resources. Using mathematical equations allow us to analyze the problem systematically and determine whether the available resources can satisfy the production requirements. These equations form the foundation of our linear algebra model and will later be solved using Gauss elimination and Gauss-Jordan methods. Now, we convert the system of equations into metric forms. In linear algebra, a system of equations can be written as AX equal to B. Matrix A is called the coefficient matrix because it contains all the coefficients from the equations. Matrix X is the variable matrix, which contains the unknown variable x1 until x5. Matrix B is the constant matrix, which contains the values on the right-hand side of the equations. For this project, matrix A consists of 4 rows and 5 columns. Therefore, it is a 4 times 5 matrix. The variable matrix X is a 5 times 1 matrix, while the constant matrix B is a 4 times 1 matrix. Thus, the number of equations is m equal to 4 and the number of variables is n equal to 5. Since m less than n, the system is known as an underdetermined system because there are fewer equations than variables. In many cases, an underdetermined system may have infinitely many solutions if the system is consistent. This characteristic will be further analyzed by the next presenter when solving the system using Gauss elimination and Gauss-Jordan methods. Thank you.
My name is NURALISSA binti SUHAIMI and my metric number is 307153. For question 3, we solved the system of linear equations using Gauss-Jordan elimination. After performing row operations, we found that the system contains 5 variables but only 4 pivot positions. This means there is one free variable. We let x5 equal to t, where t is a real parameter. From back substitution, we obtain the general solution. x1 equals 40 minus 2 over 3t, x2 equals 35 minus 2 over 3t, x3 equals 15 plus 1 over 3t, x4 equals to 10 and x5 equals to t. Since t can take any real value, the system has infinitely many solutions. For question 4, we determine the consistency of the system using the rank theorem. We found that the rank of matrix A is equal to the rank of the augmented matrix AB, which is 4. Since both ranks are equal, the system is consistent. However, the number of variables is 5, which is greater than the rank. This means rank A is less than n, so there is one free variable. We assign x5 equal to t, where t is a free parameter. Therefore, the system has infinitely many solutions because the solution depends on a free variable.
So good morning everyone, my name is Muhammad AFIF LUTFI bin Muhammad AZRAN. Today we are exploring the fundamental subspace of a key system matrix A, and looking at how its dimensional qualities form the backbone of our system structure. As you can see on slide, which corresponds directly to the work we began with our original 4 times 5 coefficient matrix. By performing full Gauss-Jordan elimination, we reduce this down to its reduced row echelon form, or PRIF A. Look closely at the PRIF. We see pivots column 1, 2, 3 and 4. This immediately tells us that the rank of our matrix is 4. From this PRIF, we can accept two vital subspace. First, the row space basis, spanned by the non-zero rows of the PRIF matrix, gives us these 4 distinct vectors. Second, the column space basis, since pivot columns exist in the first 4 columns of PRIF A, the corresponding original columns in matrix A form our column space basis, maps out here in our visual vectors. To find the null space, we solve the homogeneous system AX equals to 0. Using the last variable as our free parameter t, we substitute back through our pivot rows. Factoring out t and adjusting to integers gives us our final null space basis vector: -2, -2, 1, 0 and 3. The calculation demonstrates the rank nullity theorem perfectly. The theorem states that for any m times n matrix, the rank plus the nullity must equal n, which is the total number of columns or variable in our case. But what does this mean in practice? In our practical model, the Cafeteria food distribution project, our 5 structural variables are heavily constrained. Specifically, 4 of them are strictly bound by physical resource and system boundaries, which represent our rank. However, because of our nullity is exactly 1, we are left with 1 degree of freedom. This single degree of freedom is highly valuable. It allows the cafeteria management to schedule dynamically, generating an infinite family of valid, optimized food distribution schedule while satisfying all strict constraints.
Next, I'm going to explain the real-life interpretation. The solution has a practical meaning for cafeteria management. For example, when t equals 15, the cafeteria can produce 30 chicken rice sets, 25 fried noodle sets, 20 sandwich sets, 10 burger sets, and 15 pasta sets. This production plan satisfies all labors, ingredient, and packaging constraints because the system has infinitely many solutions. Managers can adjust production quantities according to customer demand and food popularity. This flexibility helps improve resource utilization and reduce food waste. In conclusion, we successfully formulated a real-life cafeteria problem into a system of linear equations. Using Gauss elimination, we found that the system is consistent and has infinitely many solutions. We also analyzed the row space, column space, and null space, and verified the rank utility theorem. Overall, this project shows how linear algebra can be applied to solve practical problems involving resource allocation and decision making. Thank you. Okay dah.